Howdy, kids. Good evening. Um, Hope everybody's still doing solid. And, once again, I wish we were in the classroom doing these things. But what are we to do? We're not. And so we'll continue doing things this way. I'm thinking about maybe sneaking in some, I don't know, something in these videos to give you a little extra credit or something if you were actually watching them. So maybe that'll happen. Who knows? So stay tuned. So today, let's talk about today. Let's see, back here. So we're going to focus for today is learning some things about populations of different species in an ecosystem. So, and, different factors that affect populations and how to estimate them. So, like right now, this turkey hunting season going on in Ohio, and how do the wildlife biologists know the number of turkey that are in different places around the state? They obviously don't go count them all. So it's kind of one of the things you'll be learning is how do you do that? How do you estimate a population? So that's it. We'll watch a little quick PowerPoint I'll go through with you, and then there's a gizmo activity on how to estimate populations, and then keep studying your frog calls because you're going to need to know those on Wednesday. You'll hear the frog call twice, and then you'll have a few seconds to identify what frog it is. And if you know them, it should be easy. It will only take you a second to identify the frog. So hopefully you're learning those. They're not difficult. Just play them, listen to them, and get to know them. All right. So let's talk about populations quickly. Here we go. So this is a diagram I hope you referred, just keep in your mind as you look at different things about populations. But basically this big container represents the population of anything. Again, it could be the number of turkey in the state of Ohio. It could be the number of chipmunks in your yard. Whatever the case is, the number of them is represented kind of by this container. And basically, you have things that increase the number of turkey or increase the number of chipmunks. And the thing is, the container can only hold so many. There can only be so much, and that's what we call the carrying capacity. And once that's been reached, there are things that will happen: accidents, disease, starvation, predators, just old age, and all those things will lead to what you see down here: population loss or the death of these individuals, which again will keep the ecosystem at a certain amount, again, which is what we call the carrying capacity. And they're calling this container the habitat. Obviously, again, it would be the ecosystem we're talking about: your yard or the entire state of Ohio or the country or whatever. What you can't see real well is this hole in the side of the container, and that says hunting down there. This is actually a diagram from a wildlife course and a hunter education course also. It just shows the concept of why there's hunting for different animals in different places. And what that does is by removing individuals, you can decrease these other things like disease and starvation and accidents, old age, deaths, things like that. So that's by doing that, we can avoid some of these other things and keep a species at its carrying capacity. All right. Again, some quick things. What actually is a population? It's the number of individuals of a species that live in a defined area at a particular time. That's what we call a population. It's of one species. Something that's kind of more useful, and you can really relate this too to everything going on with the coronavirus, is the idea of population density. Is how many individuals are in a specific area. And so if you look at somewhere like New York City, where this virus is such a problem, they have the highest population density in the country, the number of people that live in a certain space. And so that's a lot of times a better way to look at a population than just the number by itself, is how many are in a particular area, how many people per square mile, or, animals, plants, whatever you're talking about, square mile, square meter, however you want to define it. It's better than just saying, instead of just saying there's 1.2 million. Okay, what does that mean? If it's spread out across the whole country, not a big deal. But if it's 1.2 million in a 5 square miles, then we're talking about a different thing. That's just showing you the mathematical way of looking at it. That's if we were in the classroom, we could have done an actual little quick calculation of what our population density is in the classroom. A little question here you can answer to yourself. What do you think all individuals in population are spaced out the same way? Yes or no? Of course, the answer is no. We have what's called population dispersal or dispersion, and it just kind of describes how the individuals in a population are spaced. How do they arrange themselves? Which I don't know if you can see that, it's kind of blocked by something on my screen, but 3 types of dispersion that ecologists, biologists talk about are clumped, uniform, and random. So we'll take a look quickly at those. There's a uniform population distribution, the idea that there's a regularity in how individuals are spaced out. This would be a clumped population, where you have things in specific little groups. Obviously, they're associated typically with some resource. And then this would be random, or there's really no particular reason why they're arranged the way they're arranged. I encourage you to watch this. This is a quick video. Just, it's kind of cool. Shows some different animals and things and how they arrange themselves and how their life habits work. I won't take you through that right now, but I hope you watch it on your own. To take a quick look at this picture, what are we looking at here? What type of population dispersion do you think elephants have? Are they clumped, uniform, or random? And if you said random, you would be incorrect. It's actually clumped. So they live in a clumped. Again, they're typically going to be in family groups, and they're going to be around particular resources that they need. We can also talk about something called survivorship with species. It's kind of interesting to look at them. There's, so kind of what this is showing you here, the number of individuals that survive is on the y-axis, and then the percentage of maximum life expectancy on the x-axis. So, what you're looking at here, so like for trees, a lot of individuals are surviving a real small fraction of the maximum life expectancy of a particular tree species. And so, and it just drops dramatically. So, there are, not many trees that live to even, half of their maximum life expectancy. And that just continues to decrease from there. So, basically a lot of trees are going to die at a really young age. They just don't survive. That's why, you have gazillions of seeds produced by one plant. Maybe one of them survives to be, half of its maximum life expectancy. Birds, you're looking at more of a direct kind of relationship. They're, about half the birds live about half of their life expectancy. Not many live to the maximum life expectancy of a bird. This again is in the wild. And then you look at something like humans, where, a lot of humans live to near maximum life expectancy of humans. And of course, you can think of a lot of reasons why, these things are the way they are. So, but this is what we call survivorship curve. And it just again tells you kind of how the life history, how, a species goes about building its population and surviving. And that leads us to something called R and K strategists. There's kind of just 2 different lifestyles and reproductive strategies that organisms have. R strategists. They're generally things with small bodies, really short lifespans, reproduce really quickly, have gazillions of young, and the parents don't really care for the young at all. So this would be something, for example, like a mosquito. This is a good example of that. Mosquitoes hit all these things really well. Real small, extremely short lifespan, reproduce really quick. I mean, they can lay eggs, and the eggs, emerge as adults. Well, they go through a larval stage and they emerge adults in the matter of a couple weeks, if that. Gazillions of young, and of course, the parents never see anything other than they lay the eggs, and that's it. Then, kind of at the opposite, that mouth covering behavior there. Got that down. So I've always done that. I think most people do that. Case strategists are things that, again, kind of opposite end of the spectrum. Really long lifespans, reproduce really slowly, don't have many young at all, if more than even one. And then there's a lot of parental care. So these are kind of two ends of the spectrum. Not everything is, it's not like there's a huge like one end of a spectrum and then the other end. There's lots of things that are kind of in between. But a case strategist, like an elephant, for example, is a great example of a case strategist. They live quite a long time. It takes them about, I think, 12, 13 months of carrying a baby. And they use, almost always just one baby. And of course, the parents will care for them for years. So in your mind, maybe think of what are some other K strategists that you know of, and then what might be some other R strategists. But again, there's a spectrum there too of things that are maybe even a little bit in between. So, but anyways, these are just ways to achieve a sustained population. Neither one is good or bad or right or wrong. It's just the way animal species are. Question for you here: what type of growth strategy do you think a spider has? That's correct. They are strategists. Small, short lifespans, lots of babies, little care, no care by the parents. And again, not many of them are going to survive. Of the babies that are hatched from eggs, there's not many going to survive, as opposed to case strategists, where like almost all the babies are going to survive. A substantial amount of time. All right. Things that affect a population size. Immigration, when things come into a population from another place. Births, obviously, that's going to affect the population size. Emigration, things leaving. And then deaths, obviously, is going to subtract from the population. Those first two increase population size. The last two decrease population size. But those four factors are almost always at work in any population. Some questions here. So in Cedar Grove, 15 babies were born in the year 2000. 4 residents died. What is the growth rate? There's no information given about emigration or immigration, so we know that there's 11. The growth rate is 11 individuals per unit time year, I guess, in this case. So, and then number 2, in Springfield, 70 babies were born in the year 2000. 80 residents died. What is the growth rate? It's -10. So one of these populations is decreasing, one's increasing. A couple ways to graph or look at population growth. On the left, we have what's called exponential growth. I'm sure familiar with these kinds of things from math. Where you have small number of individuals, and then it just gets to the point where it's increasing at a really rapid rate. So you think of like bacteria, where you'd have 1 and it divides, 2, then 4, then 8, 16, 32, 64, 128, it's taken off. That's called exponential growth. That's also called a J curve because it's shaped like a J. And this kind of happens at initial stages of population growth when there's enough resources for a bunch of individuals to survive. Eventually, what happens is population takes on this shape where the growth levels off, and at that point, it's what's called a S curve. And that's once resources start to become more scarce versus unlimited resources, what you would see here, at least for the number at that point. And this eventually is what happens to almost every population. It's going to level off and have what's called logistic growth, or an S curve. You think that an ecosystem will allow a population to grow larger and larger forever? And the answer there is no. Eventually, again, it's going to level off at what's called the carrying capacity. If you go back to that very first picture I showed you with the big container, which represented the carrying capacity, there's only so many definitions here: the maximum number of individuals in a population that the environment can support at a particular time. That video actually doesn't work. I don't know what happened there. They changed the link or something on me, and it takes you to something about renting apartments. I don't know. If you're really bored, take a look at that. And then this idea of something called limiting factors, the things that will keep a population, not growing, to keep it at a certain point. And they're divided up in two categories: what's called density dependent limiting factors. And this is exactly what it means. The factor is dependent on the density of the population. So the more dense the population is, the more these things are going to limit the population. Here's some examples of them. Predation, competition will increase when there's more density of the population. Parasitism increases. Disease, again, we talked about that. You've seen this, man, right happening in our world. Something that could more affect your life than this idea of how disease is more of a limiting factor when the population is dense. And that's why this COVID-19 coronavirus is such a big deal in areas where the population is dense. Just look at anything. Look at the country. See, New York City, some of the other bigger cities, Chicago, Detroit, even in our own state. Just look where the most of the cases at. They're in Cuyahoga County in the Cleveland area, Franklin County down around Columbus area, a little more in Youngstown, Toledo. It's just an example that you can look to see this, that this is such a obvious and true thing, that disease becomes more of a limiting factor when the population is dense. Same with food, same with shelter. The more dense the population is, the more these things are going to affect the going to limit the population size. And then we have what's called density independent. These things aren't going to have anything to do with the density of the population. They're going to happen regardless of the population density. And these would be things like crazy weather events and natural disasters. Like if there's a earthquake, the density of the population doesn't affect whether or not there's going to be an earthquake. It just happens. Certain weathers, tornadoes, whatever. Right. So these things are not dependent on the population density of whether or not they're going to be a factor. Really good video here to watch. Also, it's kind of cool. Just goes through some things with populations and some people, how they study fish populations and what can limit the. It's a great example. It's from one, like a Great Lakes kind of ecosystem. So, all right. Here's the last thing I'll tell you though quickly. If you want a couple bonus points, send a remind text to me today. Hopefully you're watching this. By today, I'm referring to Monday at, 1 o'clock. And if you do that by, 1:15, I'll give you a couple bonus points. Just text says, hello, bonus points, yay, whatever. And don't tell anybody that's not watching this, because that's just not cool. Doing that for you. If you're watching the videos, trying to learn things from them. That's for you, not, any of your friends that aren't watching them. So, okay. I'll get some more information to you also about the frog call quiz that's going to be on Wednesday. How we'll do that. But, for now, just work on this population stuff and then practice some of your learning those frog calls. And have a good day.